Hello guys and welcome to a new video in physics. In this video we will complete lesson 2. We reached to the subject recoil. So in previous lecture we talked about conservation of momentum. So conservation of momentum can be used to explain recoil. For example, consider two people on inline skates, skater C and skater D. So let's suppose here we have two people. The first one skater C and the other one is skater D. Assume the skaters start at rest and experience no external forces. So let's suppose that here the two people are starting from rest. Skater C gives skater D a push. Now both skaters are moving in opposite directions. When skater C pushes the skater D, so they will moving in opposite direction. So here the skater C will move in this direction, and the skater D will move in this direction. The total momentum of the system was 0 before the push, so it must be 0 after the push. Therefore, we have a law here which is mcvc final equal to minus mdvd final. The m here that's represent to the mass for the skater C and the final velocity for the skater C. That's equal to minus the mass of the skater D multiplied by the final velocity for skater D. A rocket and its fuel form a closed, isolated system. When the fuel and oxidizer combine in a rocket motor, the resulting hot gases leave the exhaust nozzle at high speed. We know that in a rocket, the rocket has a fuel. So when the fuel combined with the oxidizer in the motor, that will result a hot gases. So these hot gases leave the exhaust nozzle at a high speed. So by the law of the conservation of momentum and Newton's third law of motion, this results in the rocket being propelled forward because of the hot gases that left the exhaust nozzle at high speed. That will result the movement of the rocket forward. So to make that clear, we have here an example problem number 4. An astronaut at rest in space fires a thruster pistol that expels a quick burst of 35 gram of hot gas at 875 meter per second. The combined mass of the astronaut and pistol is 84 kilogram. How fast and in what direction is the astronaut moving after firing the pistol? So as we learned in every question, in the beginning we will write the noun and the unknown from this question. So the noun we have here from the question, in the beginning we have the mass of the astronaut, which is equal to 84. So mc, we will represent the symbol of the astronaut is C. So mc equal to 84 kilogram. Also we have here the astronaut fires a thruster pistol that expels a quick burst of 35 gram. So here we have the other mass, which is equal to 35 gram. So md equal to 0.035 kilogram. We wrote this number like this because we convert the 35 gram to the kilogram. So when you convert the unit gram to the kilogram, you should divide it by 1000. Also the noun that we have in the question, an astronaut at a rest. So because of the astronaut at a rest and the pistol in the rest, so we have VC initial equal to Vd initial, which is equal to 0. And here we have the hot gas, the velocity of the hot gas that's equal to 875, but in another direction. So Vd final that's equal to minus 875 meter per second. And here we have how fast and in what direction is the astronaut moving after firing the pistol. So we need to calculate velocity, the final velocity for the astronaut. In the beginning, we have our law, which is equal to P initial equal to P final. So P initial, because here we have the velocity of the astronaut, Vc, and Vd equal to 0, so the momentum initial that equal to 0 also. So we have also P final. P final equal to PC final plus PD final. When you move PD final to the other side, so that will be a negative. So our law will be PCF equal to minus PDF. In previous lecture, we learned that P, the momentum, equal to the mass multiplied by the velocity. So PCF, that we can replace PCF by MCVCF equal to, here we have the minus, and PD final that equal to MD VD final. From this equation, we need to calculate VC final. So you can multiply the two sides by MC. So our equation will be VCF equal to minus MD VDF over MC. After that, we will write the numbers. So here we have minus MD, we have it in the question, which is equal to 0.035 kilogram multiplied by the velocity. So it's minus 875 divided by 84, which is the mass of the astronaut. By using the calculator, the final result should be positive 0.36 meter per second. Now here we have another problem or another question, which is what if the same astronaut in example problem 4 had a mass of only 62 kilogram? What would be the final speed of the astronaut? So here we have just a new mass for the astronaut with the same numbers. So in the beginning, we will write the noun and the unknown for the question. We said that the initial velocity equal to 0, and we have the new mass for the astronaut, which is equal to 62 kilogram, and we have the mass, I'm sorry, the mass here we have it, which is equal to 0.035 kilogram. So after that, we will write our equation, which is we need to calculate the final velocity for the astronaut, which is equal to minus md multiplied by vdf over mc. So now we will write the number. The mass, we said that it's equal to 0.035 kilogram multiplied by 875 meter per second over 62. By using the calculator, the final result should be 0.49 meter per second. Now we have a conservation of angular momentum. Like linear momentum, angular momentum can be conserved under certain conditions. So the law of conservation of angular momentum states that If no net external torque acts on an object, then its angular momentum doesn't change. This is the law of conservation of angular momentum, which is L final equal to L initial. This is the law of conservation of angular momentum. The final subject that we have in this lecture, we will talk about tubes and gyroscopes. So when a tube is vertical, there is no torque on it, and the direction of its rotation doesn't change. But if the tube is tipped, as shown here, a torque tries to rotate downward rather than tipping over. However, the upper end of the tube revolves or processes slowly about the vertical axis. What does that mean? To know or to make this clear, we will see this video. Now here we have a gyroscope, and as we said, when a tube is vertical, there is no torque on it, and direction of its rotation doesn't change. But if the tube is tipped, a torque tries to rotate it downward, rather than tipping over. However, the upper end of the tube revolves or processes slowly about the vertical axis. Until here, we reach to the end of our lecture. See you soon in another one, inshallah.